Hello, you're welcome. All right, so now before us is a topic, all right, so we're going to be treating in this tutorial, and that is electromagnetic induction. Okay, so what's electromagnetic induction? Electromagnetic induction is defined as a process by which electricity is generated in a conductor by the change in the magnetic flux linking the conductor. Okay, um, there are different ways through which electricity can be generated. We've actually talked about electricity that is generated through friction. Now this one here, which is electromagnetic induction, is a form of electricity generated when the magnetic flux linking a conductor changes, and I'm going to illustrate that. Okay, so let's say you have a conductor in form of a coil, right? Coil of wire. All right, so now this conductor is not connected to any voltage source, but rather it is connected across a galvanometer. Across a galvanometer, right? Excuse me. Now the person that actually conducted this experiment is Faraday. Okay, so you have a galvanometer, right? Now this conductor already connected across a galvanometer, right? Doesn't the galvanometer doesn't show any indication there is a current flowing through it. Then when you now bring bar magnet, a coil, a bar magnet, close, move the bar magnet around this coil, this coil of conductor. Now it is being noticed that the galvanometer actually deflects. So the movement of this bar magnet around this conductor actually causes current to be generated, and such is what a electromagnetic field is all about. So this electricity was generated by the movement of magnet, and we know very well that a magnet has magnetic field around it. All right, magnetic field around it. So this magnetic flux, right, a magnet has magnetic flux around it. So this magnetic flux that links the coil, as it changes due to the movement of the magnet, electricity is actually being generated, and that is electromagnetic induction. All right, so now we'll continue. We are going to look at Faraday's laws of electromagnetic induction. Now it was Faraday that actually conducted this experiment. He was the first to investigate the electricity that is generated due to the change in magnetic flux linking a coil. So after his investigation, he stated the law of electromagnetic induction. All right, so this is what you're going to state now. Now the law, Faraday's laws of electromagnetic induction state that when magnetic flux linking a coil, when the magnetic flux linking a coil changes, an EMF will be generated in the coil, and this EMF is called induced EMF. All right, so this is Faraday's first law. So when the magnetic flux that links the coil actually changes, then induced EMF is actually being generated. Now according to him, in his second law, he actually stated that the magnitude of this induced EMF is proportional to the rate of change of the magnetic flux that's linking the coil. So the higher the rate of change of the magnetic flux, the more induced EMF is produced. All right, I hope that is well understood. Now before we look at, so that's the two laws of Faraday. These laws now actually generate a formula for us. Excuse me, generates a formula for us. Now we're going to generate a formula. So according to Faraday, the EMF is being generated in a coil when there is a change in magnetic flux. This is a symbol of magnetic flux. change in magnetic flux with respect to time. Change in magnetic flux with time. Okay, now that's according to what he said, but the formula from Faraday's laws, okay, of electromagnetic induction is actually given, okay, in full. It's written in full this way: minus, okay, n the flux, okay, differential change of flux all over the, okay, with time, differential change of flux with time. Now I will illustrate, okay, these parameters. So now, and here, okay, represent the number of turns of the coil, number of turns of that particular coil. All right, while the flux, the T, all right, okay, represent the rate of change, okay, in the magnetic flux, linking the coil. So according to him, the more this change, okay, the more this change actually, the more of this change you have, the more EMF you're going to have. Now the question now is, from this formula right here, okay, why am I having minus? What is this, the essence of the minus sign, right? Now the essence of the minus sign is what you're going to discuss, okay, as we look at the next law, known as Lenz's law. Okay, Lenz's law actually tells us why we have that minus. Now according to Lenz's law, Lenz's law states that the induced EMF, okay, in a coil flow in a direction to oppose the motion producing it. All right, so which simply means that the induced EMF is always in opposing direction with the change in flux. And in physics, anytime we represent opposing direction, okay, when two things are equal and opposite, we use negative sign. So this particular negative sign here that is found in Faraday's laws, okay, law of electromagnetic induction is due to Lenz's law. So we say that the induced EMF is always in opposite direction with the change in flux that actually produced it. Okay, so please take note of that. That is Lenz's law. Now we're going to look at different types of electromagnetic induction. Okay, electromagnetic induction is divided into two types, okay, as discussed below. We are going to look at what is known as self-inductance. Okay, now this is the type of inductance where induced EMF is generated due to change in magnetic field of a coil, which is brought about by the varying its own current. So now, self, as the name implies, a coil can actually induce EMF in itself, all right, when the current in that coil actually changes. How does it work? Now let's look at how it works. If I have a diagram here, okay, let's see how it works. Okay, so let's say I got a coil. Okay, now I got a coil, then I don't bring magnets to this coil. The only thing this coil have is just it has an alternating current, okay, probably a current that actually changes, that is actually moving through. So the current of the coil changes with time. All right, it changes, the current changes. Due to the change in current, right, then definitely there will be a change in flux around the coil, because you know very well that when we treated magnetic effect, the magnetic effect of electric current, we already know that electric current actually produce magnetic field. So if electric current changes, magnetic field changes. So for this coil to have a current, it simply means that it has magnetic field around it. And if the current changes, the magnetic field changes. Okay, and that change in magnetic field actually uh, give rise to an induced EMF, which of course is self-inductance. All right, so it is an induced EMF in that is actually generated in a coil due to the change, okay, due to the change of current, okay, the change of current of that coil, okay, with respect to time. So now, so invariably now for self-inductance, all right, the EMF that is actually induced, all right, is given by the formula L minus L change in current, the I with respect to the T. All right, so now of course you know the essence of the negative sign. We've talked about that. Now this L now is actually the constant now known as self-inductance. Self-inductance. While of course the the I with respect to the T becomes the rate of change rate of change in current. Okay, rate of change in current with time. Okay, the rate of change in current. So please take note of that. All right, so that's what we have here. Now we're going to talk about mutual inductance. Okay, now what is mutual inductance? The name implies mutual, right? That means there are two coils this time around. Now mutual inductance is a process whereby induced EMF is generated in a coil by varying the current of another coil. Okay, close, that is very close to it. Now the diagram of mutual inductance is shown below. So this is what this mutual inductance, right? You have two coils. Okay, one coil was actually brought close to another coil that has current, okay, current connected to it, current source connected to it, and this current source actually changes. Okay, so it's called mutual inductance because it's an induced EMF in the coil due to the change in current, okay, of another coil. So by bringing, I have two coils here, L1 and L2, right? So L1 is actually have already self-inductance due to the change in current. Okay, so this self-inductance actually produces flux, all right, produces flux, and that flux now is now being coupled to L2, so that's mutual. So the change in flux of this L1 is now being transmitted to L2, now uh, which now causes L2 or causes induced EMF to be generated in coil 2, L2, right? So please take note of that. And of course, by formula, okay, if you want to, for mutual inductance, the induced EMF, right, is still gonna be given as minus M, then the I the I1 all over the T. Okay, so I use I1 to represent the current of that very first coil. Then the M, this constant M is actually what we now know as mutual inductance. So this is mutual inductance. All right, so I hope that is well understood. Okay, we proceed. Inductor. So now let's discuss inductor. An inductor is a device that stores energy in magnetic field when it is being supplied with an alternating current. So an inductor, okay, is a device, of course, in form of a coil. What it does is that it stores energy in magnetic field. So when it's you supply with an alternating current is a current that actually varies, okay, that varies with time. Then an inductor stores energy in magnetic field. So an inductor is simply a coil. So a coil of wire of many turns. So anytime it's either you call it inductor, all right, or you call it coil, all right. This inductor. There's a symbol, the electrical symbol of an inductor. Let me draw that again. So electrical symbol of an inductor. Okay, so it's a coil of wire. So inductor becomes a device that stores energy, and that energy is stored only if you supply the inductor with, okay, an alternating current. All right, it stores energy in magnetic field. Okay. All right. So now, an inductor is a coil of many turns, okay, which stores energy when supplied with alternating current. Now, the amount of energy an inductor stores depend on its inductance. So every inductor is being measured there, okay? The amount of energy or the value of an inductor is measured based on its inductance, right? Now the symbol used in representing the inductance of an inductor is L. So L is what we actually use to represent inductance, okay? And the SI unit of inductance is Henry. So which simply means that, okay, I can use the L is the symbol, okay, for the inductance of this. So and the inductance is measured in Henry. Let's say L here is 20 Henry, okay, Henry H. Okay, so inductor is also a component, an electrical component, so please take note of that. All right, so let's proceed. Now inductors, okay, the same way we can connect uh, resistors, capacitors in series and in parallel, inductor also can be connected in series and parallel. So now this is inductor in series. Okay, so of course inductors connected in series, all right, you can actually evaluate the total inductance, okay. So if you have inductors connected in series, to evaluate the total inductance is just to add up the individual inductors, right? So let's say you have this, okay, so three of it, R1, L2, L3, okay, in series. So their total inductance, the total inductance is going to be equal to the addition of the three, L1 plus L2 then plus L3, okay. Of course, in parallel, okay, so the same formula with that of resistor. So the total inductance, all right, is this L1, this L2, and this L3. So that's going to be equal to 1 over L1 plus 1 over L2 plus 1 over L3. Okay, so for parallel connection, all right, so series connection, parallel connection, we talked about that. So then finally we look at the energy stored by an inductor, all right. Since an inductor stores energy in magnetic field, how do we evaluate the energy? Now the energy stored by an inductor, okay, is given by the formula half Li square. Of course, you know what the Li is, okay? The Li is the inductance of the inductor measured in Henry. The I is the current, the electric current, okay? The alternating current supplied to the inductor, right? So please take note of this. So I believe that that is that. Now we're gonna look at the application of electromagnetic induction. Okay. Now the application of electromagnetic induction is found in the following devices. Right. We find it applicable in an electric motor, find it applicable in electric generator, and of course we find them applicable in transformers. All right. These are electrical equipment. Okay, I think we're gonna discuss them one after the other. Let's start with electric generator or dynamo, right? Now, electric generator is of course what is used to generate electricity. Okay, basically by converting mechanical energy to electrical energy. So, electric motor is a device that converts mechanical energy to electrical energy. Now, it is made up of rectangular coil rotating in a magnetic field. Okay. So when you have a rectangular coil of wire that you place inside the magnetic field, as you rotate the rectangular coil, then definitely the according to Faraday's law, okay, that change in the external magnetic field linking the coil will cause EMF to be generated. So now let's look at types of generator. Now generator is being divided, okay, into two types. We have AC generator, alternating current generator, and DC generator. Now, how is AC generator constructed, and what makes it AC generator? Now, this is an AC generator, as you can see here. All right, this is the rectangular coil placed between two magnets, okay, north and south. Right now, this coil of wire, right, is meant to rotate in this magnetic field, okay, in this magnetic field. Now, as it rotates, it will generate electricity. The coil generates electricity due to its change, okay, its rotation. Each rotation actually creates a change in magnetic flux that is linking it, okay, since it is placed in between two bar magnets, okay, in between two magnetic fields. So now, how do I actually tap this EMF that is actually generated by this coil? Since the coil is rotating, how do I connect, okay, my EMF? How do I connect that the output? All right, that is the question you should ask. Since the coil is rotating, if I should connect a wire to get an output, probably I want to connect wire to the generator to probably power my bulb. If I connect it to the coil, this coil is rotating, can't it twist the wire? So that now tells us that the way, okay, the output is actually taken from the generator is through the means of carbon brushes and of course slip rings for AC. So what makes AC generator AC is that, all right, the output is taken using slip ring. As you can see, this is a slip ring. This two is a slip ring. Then they have carbon brushes, that is the coil. The output of the coil is connected to a slip ring, first, second slip ring. Okay, R1 is one slip ring, then R2 is second slip ring. So now the output is gotten by placing carbon brush to touch the slip ring. So the slip ring rotates along with the coil. So all you just need to do is just to press carbon brush, okay, to just touch the slip ring to make sure that it is in contact with the slip ring as it rotates. So the wire doesn't need to rotate. All it does is just it taps its current from the carbon brush. So carbon brush touches the slip ring to actually take out the current or the EMF that is generated by the coil. All right, so please take note, what makes AC generator unique is the fact that it uses what slip ring. And of course, for an AC generator, let's go to my board so that you know. Okay, as the coil rotates, EMF is actually being generated, right? Now, the coil rotates, okay? The coil rotates, then the EMF is generated. The EMF actually varies, all right, according to the position or the angular rotation of the coil. So that simply means that the EMF, okay, of generator depends on this, okay, has this formula NBA, then cos theta. Apart from the fact that, okay, this is apart from that, we know that EMF is already is the EMF, okay, is gonna be equal to the change, okay, the change in flux respect to time. Okay, so I don't want to go through this how to prove this once. Okay, from here you can actually derive this formula. So EMF is given as NBA cos theta. So the theta here represents the angle between the coil and the magnetic field, right? The angle. So it shows that as the angle actually changes, the EMF actually change. Okay, I hope I am not mistaken. Now, okay, yeah. What this actually tells us is that as the core at different angle of the core, the EMF actually changes. So the EMF generated by an AC generator, okay, of course, both the EMF and the current is actually alternating. So it's AC. And of course, this is the graph you get. At one point, it is maximum, all right. At the other point, it is minimum. So both the current, okay, actually varies with time, and the voltage also varies with time. Okay, so it is an alternating current. Why? Because it varies. At one point it is positive, at another point is what? Negative. All right, so this is alternating current. So now let's see what actually happens okay, for direct current generator. A direct current generator actually delivers direct current. And how do I achieve that? Okay, for you to actually convert a direct current generator, a, convert an alternating current generator, okay, to a direct current generator, all you just need to do is just to change one thing, okay. You change that slip ring, okay, found in the AC generator into split ring that is actually split. All right, split ring. So as you can see here, so when you now do that, you have converted the AC generator into DC generator. Now, what happened in this? If that conversion, okay, if that conversion has succeeded, right? What you have is a wave that only have the positive part, okay, but this split ring will cut out the negative part of the wave, so the wave will not have negative, but it's gonna be positive cycle, okay, throughout each period. All right, so please take note of that. All right, that is AC generator. Now we proceed. So we're gonna talk about the next device, okay, which of course is a transformer. Transformer is another device, okay, that applies electromagnetic induction. What's a transformer? A transformer, okay, is a device that actually is used to step up. Okay, we'll talk about transformer now. transformer is an electrical equipment, okay, that's either used to step up or step down. Okay, and alternating AC voltage. That's what a transformer does. Okay, it's either it steps up or it steps down AC voltage. Of course, it is made up of two coils, okay, that is mutually coupled together. Okay, one coil, we have one coil which is known as the primary, that is actually coupled by the means, okay, is wound around a core known as iron core. So now this is a symbol of a transformer. So this is, let's say, the primary core, then it's actually coupled, electrically coupled. That means they're only close to each other, right? They are not connected in any way. So this is the primary core, and this is the secondary core. All right, secondary core. Now it's at the primary core that actually that serves as the input. All right, this is where you supply the voltage that you want to step up or step down. Then you take your output from the secondary. Okay, so let's say the EMF, okay, supplied, the EMF generated in the primary is EP. Then the EMF that is actually taken from the secondary is EX. Let's say the number of turns of the primary is NX, and of course the number of turns of primary is NP, and number of turns of the secondary is NX. Okay, so we can create a ratio. The ratio says that NP, right, all over NX is equal to EMF of the primary divided by the EMF of the secondary. Okay, so it's a ratio. Number of turns of the primary over number of turns of the secondary is equal to EMF of the primary divided by. Okay, so this is transformer equation. It's really very important. Now the question is, how do I know if a transformer is a step up or a step down transformer? All right, now a step up transformer will actually step up the input voltage. Okay, input voltage, it increases the input voltage, and step it down. Okay, if a step down will reduces the output voltage, okay, will be less than the input voltage. So how do we know now if a transformer is actually a step up transformer? Okay, the only way you get to know is the fact that the secondary, okay, number of turns of the secondary core is greater than the number of turns of the primary core. All right, then it's gonna be a step down. It's a step down transformer only if the number of turns of the secondary, okay, is less than the number of turns of the primary. So that is when it will be a step down transformer. All right, so now I think I have a question here. This is a question, okay, on transformer that I will solve. Now this one goes like this: the primary coil of a transformer has N turns and is connected to 120 volt. The input is 120 volt, 120 volt VAC power line. If the secondary coil is 1000 turns and the terminal voltage is 1200 volts, what is the value of N? So we are looking for the N, okay, the number of turns, NP, the number of turns of the primary. So of course you know the formula I'm going to apply here. Okay, my formula, NP all over NX, right, equal to EP all over EX. So I'm looking for the NP, the primary number of primary turns. According to the question, the secondary turns is 1000 turns, right? And of course, EP, the EMF of the primary is 120 volts. The EMF actually taken from the taken in the secondary, okay, is 1200 volt. That is a step up transformer, 1200. All right, so of course you know what you do. You can cross multiply, right? So that simply means that NP now is going to be equal to 120, right, times 1000. That's going to be 120,000. Then now divide by 2 by 1200. Right, so I've left the NP now. Number of turns of the primary is 1200. Okay, if am I mistaken? Yes, let's see if there's a mistake I made. Okay, 120 volt is this for the secondary, right? For the primary, yeah. Okay, okay, so all right. So if that's a mistake, it's probably from my parameters. Just go through the questioners, because I suspect a mistake, because this voltage, the secondary voltage being more than the primary voltage, makes it a step up. So that should make my primary number of turns to be less than the secondary number of turns. So let me go through my solution again. Okay, let me go through my solution again. NP, right, NX, number of turns of the secondary according to the question. Let's go. The secondary number of turns is 1000. Okay, so I've written that. The primary EMF is 120. I've already written that. Okay, and the secondary EMF is 1200. Okay, I have written that. All right, so okay, all right, so see, I'm the one that made the mistake. I made a mistake. All right, primary is 1200. Okay, so 120, primary is 120, then secondary is 1200. All right, so I'm having this. Okay, well, it shouldn't be a very complicated mistake. Just go through it. So let me not spend time on going through that. Let's look at the next question. Okay, so this one goes like this. A step down transformer has a power output of 50 watt and efficiency of 80%. If the main supply voltage is 200 volts, calculate the value of the primary current of the transformer. Okay, so now this will lead me to, okay, the formula for efficiency of a transformer. Okay, efficiency of a transformer. The efficiency of a transformer. All right, the efficiency of a transformer, right, is equal to the work output by the, okay, what output of the transformer divided by the work input of the transformer. Alright, now, please pardon me, the power output. Efficiency of a transformer is actually given as the power output of the transformer, okay, all over the power input of the transformer. Power input. Then of course times 100. Alright, so now efficiency, alright, is gonna be equal to the power output of this transformer. A step down transformer has a power output of 50 watts, so this is 50 now divided by the power input, okay. Alright, and if the main supply voltage is 200 volt, calculate the value of the primary current. Now power input, alright, let me still state the formula. Of course, you know that power, okay, is always given as current times voltage, right? So the power output is gonna be equal to, the output is from the secondary, right? That the current of the secondary times the EMF of the secondary. Alright, the input, power input, is gonna be equal to the current of the primary times the EMF of the primary, okay, then times 100. Alright, now coming to solve this question, the efficiency of this particular of this transformer is said to be 80. Then the power output, the whole of this is the power output, which, okay, is given as 50 watts. Then divided by we are looking for the primary current, right? Then of course the primary EMF is 200 volts according to the question. Then of course times 100. Okay, so this cancels this, right? So I can cross multiply then. Okay, to make IP the subject, now IP is going to be equal to 50, right? Then divided by 80 times 2, 2 times 80. That's going to be 50 all over 160 if I'm not mistaken, right? Okay, so 50 all over 160. 50 divided by 160. 0.3 approximately 0.3 ampere. Alright, so I hope that is well understood. Okay, another question. A transformer is rated 240 volt. If a transformer is rated to 40 volt, simply means it will output, the output it will give is 240 volt. Okay, if the primary core is 4,000 tons, so let me write the parameters. The transformer is rated to 40 volts. That means the EMF of the secondary is 240 volts. That's what that rating means, okay? Alright, so now, if the primary core is 4,000 tons, NP is 4,000 tons. Alright, so, and the secondary voltage, okay, the secondary voltage, oh, am I mistaken? Yep, the rating of a transformer is okay, the rating of a transformer is the amount of voltage it can take. That should be the primary voltage. All right, please pardon me. So the secondary voltage, all right, the secondary voltage is 12 volts. So that's a step down transformer, 12 volts. Okay, so determine the number of turns of the secondary. So I'm looking for NX question mark. All right, so of course the same formula. NP, okay, all over NS. I know how you want to do it. Okay, you can start with NS all over NP, but there must be proportional both side of the equation. Okay, so if I'm using NP all over NX, then the other side of the equation is gonna be still the same. Okay, ratio EP all over EX. All right, so this is gonna be NP 4000 and X. That's what I'm looking for. EP 240. Then of course EX 12. So NX now, if I make it the subject, it's just gonna give me 12 times 4000. Then divided by 240. Okay, so 12 times 4000 divided by 240. So 200 tons. So NS is 200 tons. All right. Okay, so that is the end. That is the end. All right. See you in the next video. Thank you very much.